Kia ora, Robert McLaughlin here. Welcome to Lecture 2 of Week 7 for 160.204, Differential Equations 1. We're going to continue our study of linear systems. We won't actually solve a linear system of differential equations today. That will come up in the next lecture, but we will get a lot of general information about what linear systems look like and what the structure of the solutions will look like, how to recognize the solutions when you've got them. This system here, system of two ordinary differential equations. This is the tank flow model from last time, just written out the same equations again. And the important thing about this one is that the right hand side is a linear function of x1 and x2. So just like when we studied higher order equations, the linear differential equations were very important, and amongst them the constant coefficient linear differential equations were very important as well. This is going to be the same for systems. The coefficients there, the 0.08 and the 0.02, they're constants, they're not functions of t. And there's no nonlinear functions of x1 and x2. There's no term like x1 times x2, cos x1 or x1 squared or anything like that. So this is an example of a linear system. And what we're going to do is reformulate this using matrix vector notation. So I'm going to bundle those two functions together into a vector. Now, the slightly different thing between the vectors that you've met before, for example in 160.102 algebra, is that these are not going to be functions of t. So it's still got two components in it, but each component there is going to be a function of t. So you can think of it as a vector in the plane, for example, but it's moving around as t changes. Now you can differentiate vector functions. You just differentiate each component. And you get another vector function. Well, dx1 dt, dx2 dt, that's the left-hand side. What about the right-hand side? I'm going to write this as a matrix times a vector. And if you remember how to do matrix multiplication, this is just a matter of reading off the coefficients. So it's going to be minus 0.08, 0.02, 0.08, minus 0.08. So I get a 2 by 2 matrix times a column vector with two components. So I could write that as dx dt equals a matrix, 2 by 2 matrix A, times a vector. Dx dt equals ax. So this is in fact a general way of formulating any constant coefficient linear system in any number of variables. Here I have two variables, but the advantage of the matrix formulation is it works equally well with any number of variables. So as we go through and solve these systems and understand them, we will be using ideas from matrices and vectors from linear algebra. So you may need to refresh this. There is a refresher course on this in the textbook ZIL. It's in Appendix 2. But if you haven't actually studied first year linear algebra, then you might need to do some extra learning, and we can arrange some backup for that if necessary. So here's what it would look like for a linear system in any dimension. Instead of x1 and x2, I now have a vector x with n components. So I could write vector x as a vector in Rn. And I have an n by n matrix of coefficients. That tells me what my system is. So this humble system, dx dt equals ax, this describes an enormous range of possible physical behavior, and many systems, large systems, for example, large engineering systems of bridges and buildings with thousands of parts in them, can be described in this way. So a lot of the phenomena in nature come down to understanding systems of this class. We've got a differential equation, and for an initial value problem I need to specify their starting values. Could be at any time, but may as well say x1, x2. So it's basically saying vector x at time 0 is some given vector. And the solution is going to be something like a vector where every entry in the vector is a function of t. And this is a curve in Rn with parameter t. As the time changes, that point in Rn, that vector, moves around. So I can draw a little picture. I suppose n was 2. Here's my x1 axis, here's my x2 axis. I'd be starting at some point. That's x0, that's my given initial value. The differential equation tells me in which way I'm moving, because dx/dt is ax. I could work out ax and it would be some vector. And then as t increases, this vector moves around. And where it goes, we don't know until we've solved the equation. But that's a very important key idea. The solution to a system of ordinary differential equations is a curve in the vector space Rn. This would be t equals 0 here, along here might be t equals 1, along here might be t equals 2, and so on. That point slides around, moves around in the vector space Rn. So you can get a great deal of understanding of systems of differential equations by considering what these solution curves look like as curves in R2 or R3, by considering the low dimensional case first. Now, just as with higher order linear equations, we had a principle of superposition. Same thing happens with first order systems. So if x1 of t, so now I'm calling x1 the first solution, and x2 of t, not labeling the components, but labeling which solution I'm talking about. I've got two solutions. So is a linear combination c1 x1 of t plus c2 x2 of t. So you can, if you have a solution of an equation of this type, you can multiply it by a constant. And if you have two solutions of this type, you can add them together and you will still get a solution. Let's just check this. Let's call this x. Well, what is dx dt? I have to differentiate the left-hand side. That gives me c1 dx1 dt plus c2 times dx2 dt. Now x1 and x2 are solutions, so dx1 dt is ax1. And x2 is a solution, so dx2 dt is ax2. Rearrange that and I get a times c1 x1 plus c2 x2, that's ax. So this is the power of the matrix approach. Very simple calculations using matrix algebra give you very powerful and general conclusions. Now, these two solutions that you find, or any number of solutions, it's very important that those solutions be linearly independent. Remember the definition of linear independence. x1 up to xk, a bunch of vectors, are linearly independent if and only if a linear combination and only if all the c's are 0. This is the same definition that we had in linear algebra, where the x's were just constant vectors. Now they're functions of time, but it's the same definition. So this says you're linearly independent if the only way a linear combination of those vectors is 0 is if all the coefficients are 0. And conversely, if there is some non-zero set of c's, such that that linear combination gives you the 0 vector, then the vectors must be linearly dependent. So when we're solving differential equations, we're looking for linearly independent solutions. So let's say I've got the most general equation. So a system of n first order equations. N might be 1,000,000 or something if I have a large system. What does the general solution look like? The general solution is going to be C1 x1 plus ... plus Cn xn, where these solutions here, they'd be, just as earlier, they'd be called a fundamental solution set. X1 to xn have to be solutions, and they also have to be a linearly independent set. Linearly independent solutions. So if we can find not just one solution but n of them, and they're linearly independent, then we know that we have found all possible solutions to the differential equation, and we also know we'll be able to find a unique solution to every initial value problem. So this is so far just some definitions. It's not telling you how to actually find these solutions. And I didn't tell you how to check if your functions are in fact linearly independent or not. Well, there is a way with matrix algebra to do that using a determinant, and in this case, in the differential equations context, it's called a Wronskian, just as we had earlier. So the Wronskian, let's call it W. It's a function of n vectors. It is a determinant of a bigger matrix. What you do is you take those n vectors and you stack them together and put them in as the columns of that matrix. So that's an n by n matrix. So you can form its determinant, and that set of vectors is linearly independent if and only if the Wronskian is non-zero. If the Wronskian is 0, they would be linearly dependent. Now, we're not going to do large systems. If you had an actual large system, you wouldn't be doing it by hand. We're only going to do 2 by 2 and 3 by 3 systems so that the algebra doesn't get too out of control. But it is nice to have the theory so you know how it works for systems of any size.